Today's webinar is going to be for introduction to shallow foundation, and the intention for today's course, and at the end of the session, you should be able to understand what are the basic types of foundation, a bit of introduction into different types of design philosophy, introduction to calculation of bearing capacity for sandy soils and clay soils, and the settlement calculation. Before I begin, I would also like to share that this is going to be a bit of a refresher or review that should help you in your maybe a college viva or interview preparation if you're applying for a job company. And in addition to it, let me share that the equations which I'm using for this, as you must be aware of, there are various kinds of methodology as well as codes. So for this one, I am referencing the AASHTO guide, which is American Association of State Highway and Transportation Officials. So if you see a bit of variation with the factors, please don't be worried if it is different from the typical textbook, for example, which uses Tarzagi's equation. So these are the, and I will also indicate as during the session that where are the various differences. And as Divya mentioned, please add your questions in the chat. So we will discuss that at the end of the session. So to begin with, yeah. So for foundation, and I will be addressing foundation as substructure, and the structural elements would be classified as superstructure. So as you know, for any kind of superstructure, be it building, roads, highways, it has to be founded on soil so as to transmit the loads to the soil. In easy way, we can classify foundation are the substructure components which transmit the superstructural loads to earth or ground in a way that it does not undergo deformation that would cause settlements. And when I say it does not undergo deformation, it does not mean it is zero. And then the idea of design or tolerable settlements come into picture, which we'll be discussing towards the end. So moving on, if you must be aware of, the foundations are basically divided into two types: shallow foundation and deep foundation. So shallow foundations are typically founded at depths of 1 meter, 2 meter, 3 meter, in the extent where soil can be excavated. In case there's a weak soil layer extended till, or compressible soil layer extended till 10 meter, the excavation is not possible. So we go ahead with pile foundation. In today's session, we will be talking about shallow foundation, which are typically located at depths more than 0.5 meter. And the various shallow foundations are, as you can see over here, strip footing, where length is typically very much longer than the breadth, and it is used, for example, in case of putting foundation for walls. Spread footing or isolated footing, it is used for carrying the isolated column loads. To give an example, for example, there is a pole or the staircase or those kinds of things. Combined footing is the case when we have too many spread footings which are very close to each other, so we combine them. And in the similar understanding, raft foundation is for the case when there's a large area of loads and we want to distribute it as without causing any settlements. Moving on, I would also like to introduce you to the two theories for designing footings: rigid as well as flexible. So there's no perfectly as such rigid or flexible foundation, and the assessment of that is done on the basis of elastic modulus, section modulus, as well as the subgrade modulus. But in a layman's term, if I have to share what a flexible foundation would look like, so if I have to say there's a tank resting on a ground, so there will be a uniform load which is acting on that soil. If I am to recall a uniformly loaded beam, you will see that at the center, at the bending moment diagram, there is maximum deflection. and as well as the shear forces will be high at both the edges. So if I am to design a flexible foundation, it should have maximum bending at the center. So typically, tank foundations are designed with that theory. When it comes to rigid foundation, for example concrete, and we want the entire footing, the entire foundation or structure to not have that flexibility but settle uniformly, so we will have rigid foundation designed for it. Yeah. So coming on to the basic, for example, if I'm given the assignment of designing a foundation, the various components that I should be needing to design that would be understanding of the loads, which comes from the type of structure or the input that you will get from the structural engineer. The second one being the necessary soil parameters that typically a geotechnical engineer or a geotechnical investigation report will share with you, which is the cohesion, the friction, and the other values. The third part, which is the design of shallow foundation, which would consist of calculation of the bearing capacity, calculation of the settlements, having sliding resistance so as to manage the horizontal loads, as well as the overturning load so that our foundations are safe against overturning moments. So we'll also discuss a bit into the types of loads. The types of loads which are acting on foundation can be broadly classified as horizontal, vertical, as well as moments. And when we talk about the vertical loads, in basically we can term that into dead loads and live loads. And as you can see over here, there is a bit more description into the types of loads which are typically encountered in a plant or a process facility, where there are various kinds of loads, and I've also added the direction in which they are divided. And in the various load combinations, we take, for example, dead load plus live load, dead load plus live load plus wind, with various factors, and also in addition of extreme cases, extreme environmental loads such as earthquake loads or other environmental loads. So moving on to, as you must have also come across in the steel structure design, there is LRFD design and the traditional method of designing, which is AST or allowable stress design. In allowable stress design, this is typically the most used or the historical way of you doing the geotechnical design, in which a blanket factor of safety is used, which is in the range of 2.5 to 3.5. And to be on the conservative side, because we know with assessment of the geotechnical factors, as soil is very variable, we tend to use factors, for example, in the range of 3. And it is as it is mentioned, it is quite simple and more conservative. There's another or newer methodology, which is using the load resistance factor design, which includes the use of partial resistance factors, where these are applied on the strength as well as the resistance. Coming to the bearing capacity calculation, and the formula which you are seeing over here is what I have taken from reference from the Astro design. So this is a typical formula for the calculation of bearing capacity at a particular depth in soil. I would also like to share the calculation of Q, or the load which the bearing capacity has to resist, comes from the superstructural loads, which is force upon area, which is the superstructural loads. For example, a column load existing in sharing a load P on the foundation divided by the area of footing, as well as we also have to consider the load due to the above section of soil at the depth of foundation, which is coming from the footing. So typically my factor of safety is bearing capacity, which we are calculating from this equation, divided by the load which is being applied from the superstructure. And as I mentioned, the factor of safety should be in the range of 2.5 to 3. While calculating the bearing capacity or the shear strength of soil, the various factors are taken into consideration, as the cohesion as well as friction. In case of sandy soils or granular soils, the cohesion is taken as 0, and in case of cohesive soils, the angle of friction is taken as 0. So these are uh, for purely cohesive and purely granular soils. But in case of mixed soil, both C and phi will also be present. I would also like to discuss here, or maybe discuss in detail, the various types of soil before we go into the description for their calculation of bearing capacity. So the soils can typically be divided into three types, which is granular soil, which consists of gravel and sand; fine grained soil, which consists of clays and silts; and organic soil, which consists of peats and loams. And if you recall, the gradation of these soils are on the basis of the sieve analysis, for which the granular soils are typically the ones which pass through the 2 millimeter sieve, and the fine grained soils are ones which are passing through the 0.05 millimeter sieve. And for organic soils, it has to be less than 0.002 millimeter. These are a couple of just bench markers for these classification of soils. So in the calculation of the bearing capacity, the formula is CNC, as you must have seen in the Terzaghis way, CNC plus Q and Q. Here Q is gamma DF, as you can see here, and zero point 0.5 gamma B NC. And as you can see, there are various factors which are NCM, NQ, and N gamma, which are related to the shape factor, depth factor, inclination factor, and the effect of water table. So beginning with the effect of water table, and I would also like to point over here, the as in comparison to the Terzaghis, we're using gamma dash. Here we are using gamma, which is the moist soil weight or the bulk density. And when we take into consideration of the impact of groundwater table, which is CWC, this will be as we see mentioned here. For example, in the case of depth of water 0, which is at the ground level, the CWQ factor is 0.5, which means that the density of soil will be half, which is typically a thumb rule when we calculate the submerged soil weight, which is the density of soil minus density of water. Again, these are very crude numbers, and if you want to use, we can use the exact submerged soil weight as well. So moving ahead with the factors which affect the bearing capacity calculation, which is the location of groundwater table. Moving on to the shape correction factors, as you can see over here, depending on the angle of friction, the surcharge and cohesion and the unit terms SC, SY, S gamma, which are affecting my NC, NQ, and N gamma, have to be taken. Going ahead with that, and the depth correction factor, which is for the embedment zone, depending on the DF by B ratio, we calculate the DQ, as well as the inclination factor. For example, the footings which are resting on slope, we take into consideration the inclination factor. So the end product of calculation of all of these impacting factors, we calculate NC, NQ, N gamma, and plug in all these parameter values and put it in the equation to calculate my bearing capacity, allowable bearing capacity, divided by the load which is coming from the superstructure, and thereby calculating the factor of safety, which as mentioned should be in the range of 3. Another element I would also like to point out here, in the calculation of the stresses acting on the foundation, where we calculate P upon A, where A is the area of foundation. In real world, the loads might not be acting directly at the center. In case of eccentricity, the effective area that we use for the calculation for the area, so this is for the rectangle foundation, where the effective area is being reduced into B minus 2 times the eccentricity. As you can see over here, the eccentricity in the application of load in the breadth, as well as eccentricity in the application of load in the length of foundation, which is being factored over here to calculate my new dimensions, which are L dash and B dash. So my new calculation of stress would be load coming from column, which is P, divided by L dash into B dash. Okay, now moving on to the other element for our foundation design, which also becomes the criteria for selection of foundation, which is settlement. So total settlement is summation of elastic settlement or immediate settlement, consolidation settlement or primary settlement, plus secondary settlement. So for our two different types of soil, the settlement is observed differently. And I would like to go back to the basics of our uh, soil formation. So our soil is consisting of the solids. So basically it's the volume of solids plus volume of voids, where volume of solids represent the actual soil skeletal or the particles, and the volume of voids is divided into volume of voids occupied by water, volume of voids occupied by air. When we talk about the immediate settlement, the volume of voids of air is the one which is getting compacted. Whereas in the primary and the secondary consolidation, the volume of voids of water is getting lesser. In sand, we observe immediate settlement and to share because the surface area for sand particles is larger, so it does not have the water retention capacity. Whereas we remember in the fine grained soils such as clays and silts, because of the larger surface area, the water holding capacity is more. Hence, the dissipation of water is not very quickly, which leads to building of pore water pressure. In a very simple term, for example, there are loads which are being applied to a soil which is sandy in nature. There will be immediate settlement observed, and that would consist of, say for example, we will see that in a duration of 7 days. But if we have a clay soil or fine grained soil, we will have some initial immediate settlement, but that will not be very much or can be neglected as compared to the primary consolidation, which takes a couple of months when the pore water pressure is slowly dissipated, and secondary consolidation is which can continue up to couple of years or decade. So the various types of settlements which are taken into consideration while designing a foundation is maximum settlement. The second one being differential settlement, which is most critical. And why I'm saying it is critical, because for example, if my entire structure is going to settle all together, then it will not cause distortion at individual component level. But if there's a differential, for example, one edge of the foundation has raised higher as compared to other, it would lead to overturning. And in the similar way, angular distortion is calculated for design of tank foundation, which is another way of uh, expressing the differential settlement. Coming to the also, I will also want to share maybe a bit in detail about the consolidation in clay soil. So for example, in case of clay soil, when there is poor water pressure, when we apply loads, so to begin with, for example, there is a soil with only air particles. We apply a load gamma z, delta z, then the soil particles will compress, and the load will be taken by the soil skeleton. And if I am applying effective load, it will be taken by the soil skeleton. So my total load will be sigma z plus delta sigma z when there is only air. But in case of saturated soil particles, for example, at present state, there's soil particles and there's water available in the system. Initially, there's a load which is being applied, so no further change on that, sigma z. But when we apply another additional load, for example, sigma z naught, then if then that additional load will be taken up by, because the soil particles cannot rearrange themselves very quickly, so that additional load will be taken by what, the water which is present in the voids, which leads to increase in the pore water pressure, which we also denote by terminology u. So you will see that the entire, so there will be increase in the pore water pressure. But eventually, as the water dissipates and the pore water pressure becomes less, the soil particles rearrange and it will be taken up by the particles. Hence we say that clay soils observe. So as you can see over here, in the first stage of settlement is the elastic settlement, then comes the consolidation and creep, which are characteristic in the clay soils. So this is a very basic chart which will help us understand what are the various soil types undergo and what are the kinds of settlements they undergo. For example, starting with rock, since it is a granular soil, so it will have immediate settlement, but no consolidation or no creep. In the similar lines, the gravel, being a granular soil, will have immediate settlement, no consolidation or creep observed. Sand, also being a granular soil, we see immediate settlement, no consolidation. Coming to our fine-grained soils, which is silt and clay, and again, I'm saying the undrained condition because there is an existence of poor water pressure. So immediate settlement almost to none or negligible. Consolidation, yes. Creep, yes. For clay soils, as it is also a fine-grained soil, there will be a consolidation as well as creep. And similarly, on the lines of organic soil, we have consolidation and more of creep. So a very elementary method for calculation of elastic settlement, which is applicable for sands. And again, this is basically derived from Hooke's law, where sigma is elastic modulus into strain, and then we calculate the deformation. So typically the settlement or delta H, which is the settlement, is the stress divided by the elastic modulus into the height of my soil layer. And again, I would also like to share there are lots of calculation formulas such as Bosnisk, which is used for calculation of the vertical stresses at a particular depth. As I was mentioning, the calculation of vertical stresses is done by various methods. Bosnisk, or a very elementary method which is used, which is 2:1 vertical, 1 horizontal load dissipation method, 8-degree dispersion method, and you must have also come across the Schmerton method in the textbook. So in this case, we will talk about the distribution, vertical stress distribution beneath a rectangular footing. And you can see there is a stress bulb, which is typically for a rectangular footing or square foundation, which we are taking typically at the depth of 1.5 p, and the various stress bulb parameters are mentioned over here. And then we calculate sigma z at the particular depth with the formula of q into ip, where ip is being calculated with the equation as shown over here. Some more info into calculation of stresses at for rectangular footing. Coming to consolidation settlement, I would also like to point out we are taking into consideration the 1D consolidation, which is a very conservative way of approaching, because uh, the consolidation will happen in all three dimensions, but taking into consideration that the length of the footing is very long, as well as there is a lateral confinement of the soil, so the settlement is going to take place in the vertical direction. Yeah. Coming to the theory which I was sharing, that the soil can essentially be divided into solids and voids consisting of air and water. In the scenario of immediate settlement, the compression is there, which causes the immediate settlement, which is typically the characteristics of sandy soils. Whereas in the clay soils, there's reduction or dissipation in the pore water pressure, and as you can see, the volume of voids of water decreases. Coming to the condition for the fine-grained soils, so to share, for example, in a place where I'm going to build my foundation, previously it might might have been conditions of higher loads existing on it. For example, there would have been some glacier or mountains or other geological features which would have stressed my soil more than the loads which I'm going to apply. On the basis of that, there's a term which is called pre-consolidation pressure, which is being evaluated by doing the lab test on the soil sample. So sigma p is the pre-consolidation pressure which we get from the soil test, and on the basis of that we divide the soil, the clay soil, for three conditions, which is under consolidated, normally consolidated soils, and over consolidated soils. For under consolidated soil, my pre-consolidation pressure is greater than the existing pressure. For normally it is same, and for over consolidated soil uh, it is already more. And this leads to the difference in the this leads to factors in the consolidation settlement equation, as we know of. Some more description of the factors which affect the rate of consolidation, and bit more theory of the into the rearrangement of the soil particles as we apply weight. As you can see in the first diagram, so this is a soft soil layer, and for where the particles are distributed, and this is in the normal state. When we apply the weight in figure 2, as you can see, it is being pushed and water is taking the load. And you will please notice that the soil particles have not exactly rearranged a bit. So the water is taking the load. The third part or the stage where the soil skeletal starts taking the load, or let's say when the effective stress increases, is when there's the end of settlement, or the weight is completely lying on the soil particles. Coming to the consolidation test curve, which is the which you can see over here, which helps us in determining the consolidation coefficient, which is further helping us in calculation of consolidation. And as I was mentioning about the pre-consolidation stress, in when we plot this diagram of void ratio versus log stress, it is the point which is available from our lab testing, and as we draw, we get from the pre-consolidation to the consolidation, and we also see the normally consolidated as well as over consolidated soil behaviors. So going a bit more into consolidation, for the calculation of consolidation for 90%, where we use the time and the drainage factors. Not going into too much of detail, for your information, the formulas over here